I'm Sayantan Sen. I'm currently a research fellow at the for Quantum Technologies at NUS. Today I will talk about our work on testing versus estimation for index-invariant properties in the huge object model. This is a joint work with Saurabh Chakraborty, Eldar Fischer, Arijit Ghosh, Amit Levi, and Gopinath Mishra. So let us start with the notion of distribution testing. So suppose we have an unknown distribution and we can access it via an oracle where we can obtain IID samples from the distribution. And our goal is to understand some properties of this unknown distribution. So whether it is uniform or whether it is monotone or something like that. And our goal is to take as few samples as possible from this oracle to decide the property of T. So more formally, the property testing of distribution is defined as follows. Given a property P of interest, our goal is to design an algorithm or a tester that on IID sample access from the oracle representing D, outputs accept when T is epsilon 1 close to the property P, or an output reject when it is epsilon 2 far from P with probabilities at least 2/3. So again, to reiterate, our goal is to minimize the total number of samples that we take from the oracle of T. So let us start with some variants of distribution testing. First of all, a distribution D is close to the property if the L1 distance between the distribution and the property is close. Similarly, we can also define farness from a property. And when epsilon 1 is equal to 0, meaning we want to distinguish whether this unknown distribution exactly has the property or far from the property, is called non-tolerant testing, and the associated algorithm is called non-tolerant tester. And for arbitrary epsilon 1 epsilon 2, this is called tolerant testing. So it turns out that tolerant testing or estimation is generally harder than their non-tolerant counterpart. And over the last 2.5 decades, they have been extensively studied. See the book by Goldrick and the surveys by Cannon for more detailed references of the techniques. So till now, what we have talked about is that when the distributions are defined on, say, integers from 1 to n. So each sample is actually a n-bit string. So when you obtain a sample, it is easy to read through the full sample description and detect what is the identity of the sample. But suppose consider probability distribution over high dimensional spaces, for example, say n-dimensional Hamming cube. Now each sample obtained from distributions over 0 1 to the power n is actually a n-bit Boolean vector. So in order to read through a single sample, we need to read all the n bits, and this is clearly infeasible for large n. So in order to tackle this, Goldrake and Ron recently introduced the model of distribution over huge objects, or Toho model, where similar as before, we can obtain IIT samples from the distribution. But additionally, now we have a query oracle access to the samples. For example, we can query the first, second, and last in bits of the first sample, and so on and so forth. So in this model, our primary goal is to design algorithms that query each sample only on a few places. And the goal is to minimize the total number of samples as well as the total number of queries performed in an algorithm. So just to formally define distribution testing in huge object model, similar as before, we have a property P of interest, and we want to design an algorithm that given sample and query access to the unknown distribution T will output accept with probability say at least 2/3 if T is close to the property and reject if T is far from the property. But interestingly, unlike the previous case, here the notion of closeness is no longer in terms of the L1 distance. We'll use earth-mover distance to define the distance measure between the distribution and the property. So let us see what earth-mover distance is. So The variation distance or L1 distance is not a good metric for our high dimensional setting since it treats every small and big difference between two samples the same. So since we will be working on high dimensional spaces, capturing how close and far two samples are is essential for us. So for this purpose, we use the notion of Arthur distance. So for example, the Arthur distance between two distribution mu and tau is the minimum distance across all transfer schemes between two distributions where the distance between two strings in the support of the distribution will use the normalized Hamming distance. For example, in these two distribution in this picture, they are very far in variation distance, in fact maximally far, but the EMD distance captures that they are somewhat close to each other. So now comes another crucial part of our talk, namely the notion of index-invariant properties. So we call a property index invariant if we take any distribution in the property and we apply any permutation on the indices of the strings on its support, the permuted distribution will also be in the property. So this notion is different than the more commonly used studied notion of level invariance or symmetric properties. So in a sense, index invariance is a weaker notion of invariance where we are applying the same permutation across all strings in the support. So interestingly, the total number of level invariant properties in this setting will be 2 to the power n factorial, whereas the total number of index invariant properties will only be n factorial. Okay, let us first see some examples of index invariant property to gain more intuition. So for example, the property of monotonicity, whether a distribution is monotone or far from monotone, is an index invariant property. Similarly, the property of the distribution having bounded VC dimension is also index invariant. However, not all properties are index invariant. For example, given a fixed distribution Q, which is non-index invariant, testing whether the unknown distribution is same as Q is not index invariant. Similarly, the property of less than equal to is also not index invariant. So in a previous work, proved that any index invariant bounded VC dimension property can be tested using only constant queries, which is independent on the dimension n and depends only on proximity parameter epsilon and the bound on the VC dimension. And it turns out that the sample and query complexity of our tester is doubly exponential and doubly exponential in D, where D is the VC dimension bound. And it turns out that these results are tight. So a natural way to extend this result is to, if we can, instead of testing, if we can estimate the distance between the unknown distribution and the property. So in this work, we show that this is indeed possible. So given any index invariant property, we show that if it is testable using constant queries, then it has a distance estimation algorithm that also uses constant queries. So given an index invariant property P and a distribution D, we can estimate the distance of the distribution from the property using only constant number of queries that only depends on the proximity parameter epsilon and independent on the dimension n. And for this purpose, we develop a regularity-like framework for index invariant properties. Interestingly, this brings index invariant property under the umbrella of properties where constant testability implies constant estimability. And this, of course, generalizes our testing result that we saw in the previous slide. And moreover, often this regularity-like framework has a tower-like dependence on 1 over epsilon. But fortunately for our case, we show that only doubling exponential dependence on 1 over epsilon is sufficient for our purpose, which we also believe to be tight. So in the rest of the talk is divided into two parts in the next few slides. I'll briefly give an overview of our estimation algorithm, and in the second part, I'll delve into more details. So before jumping into our algorithm for arbitrary distribution, let us consider a more structured distribution, for example, a product distribution. Since the distribution is product, we can think it in terms of n marginals, and once we have the marginals, we can consider a type distribution. Now, since the property is index invariant, we can actually estimate the type distribution efficiently. And we further prove that the distance between two distributions can be approximated by their distance of the type distributions. So a natural approach to test against a distribution and the index invariant property would be to first approximate the type distribution of the unknown distribution in D and test it against all distributions in the property. Unfortunately, the query complexity would depend on the size of the property, which can be bad. So in order to bypass this, we note that although the possible number of type distributions is unbounded, the number of discretized type distribution under suitable discretization is actually bounded. And instead of testing against all distributions in the property P, we can test for all possible discretized types distribution. Now there is another subtlety coming. So since we will be considering all discretized type distributions, we might accept some type distributions that do not correspond to a distribution in the property. And in that case, we might err. So in order to tackle this, we need to detect type distributions that are indeed close to the property P. Namely, there is a distribution in the property whose type distribution is close to the type distribution that we are currently having in our hand. So for this purpose, we recall another of our result where we showed that any index invariant property that is testable in this huge object model, it has a canonical tester for this property. So once we have the canonical tester, considering a discretized type distribution, we can now run the canonical tester to detect how much close it is to the property. And together, this is sufficient for product distribution. Just to sum up, we first approximate the type distribution of the unknown distribution, then we consider all possible discretized type distributions that are accepted by the canonical tester, and then we estimate the distance between our unknown type distribution and the possible type distributions that are close to the property. And combining, we show that this is sufficient for product distribution. Now, of course, we want to solve it for general distribution. So how do we extend our approach to general distributions? So for this purpose, we prove that we can express an arbitrary distribution as a convex combination of a constant number of distributions that are similar to product distribution. So in a sense, we can write the unknown distribution D in terms of the component distributions Ti. And this is very much reminiscent of the regularity lemma in the graphs, where each Di corresponds to the partition, like the partitioning of the graph. And we prove that we can approximate lambda and Di efficiently using only constant number of queries. And this suffices for our purpose. So to sum up, we designed a regularity lemma for index invariant properties. And by the virtue of this approach, we can estimate the distance of the unknown distribution from an index invariant property. Okay, now we'll move into the second part of the talk where we'll delve into more details. So let us start with the notion of detailing. So this is crucial to our work. So this notion is motivated from the notion of partitioning for regularity lemma for graphs. So for a distribution mu and a set A, the detailing of mu with respect to A is another distribution chi over 0 to the power n cross A, whose projection on the first entry is the distribution mu. So in a sense, we are trying to write the distribution mu as a sum of its component distributions mu a. So to see it more visually, so this is a picture where we are partitioning the full Hamming cube into 4 parts. Now, once we have defined the notion of a detailing, we now consider the statistics of a detailing. So let us assume that our underlying distribution is mu and xi is one of its detailing. So the associated weight eta a corresponds to the weight distribution of xi, which is also the second projection of xi on its second coordinate. And once we have eta, we can also similarly define the notion of a type vector, which uh, captures the probability of the variable I being 1 when a sample is drawn from the component distribution mu. So once we have these type vectors for each of these variables, so we can also consider the notion of type distribution, which is a distribution over 0, 1 to the power a. Now together, this weight distribution eta and the type distribution lambda, we call them the pair, the eta and lambda pair as the statistics of the detailing chi of mu. Now, for our purpose, we need two properties of detailing, namely the property of predictability and property of inheritance. So what are these properties? Let us start with the notion of predictability. So the predictability captures the problem of estimating the acceptance probability of a distribution by a canonical tester. So just to recall what I have seen in a couple of slides back, so in a previous work, we actually proved that if an index-invariant property is testable, so there is a canonical tester for that property. And the canonical tester is extremely simple. So we get S IID samples from mu, and we sample Q indices uniformly at random from 1 to n. And we query each of these S samples on those Q indices. So in total, we have performed QS queries. And at the end, we decide based on the output of the QS queries. So this is the canonical tester. So we showed that for an index-invariant property, this canonical tester is sufficient to approximate the acceptance probability. So we consider a distribution mu to be good if most of its tuples are close to being independent. And the detailing xi of mu is said to be good if most of its component distributions are also good. So we actually prove that if the detailing xi of a distribution mu is good, we can actually simulate the canonical tester without making any extra queries to mu. So we can approximate the acceptance probability by running the canonical tester without making any further queries to mu. Now there comes the second part of our ingredients, namely the notion of inheritance. So let us start with the detailing xi of a distribution. So if the original type distribution of xi and the type distribution of xi obtained after refinement of bounded size are somewhat close, then we say that the type distribution of the refinement is inherited from the original type distribution of xi. So for example, in this picture, this is shown that on this on this top square, we are kind of like refining the space furthermore. So how do we use inheritance for our purpose? So let us consider the input distribution mu and one of its detailing chi. And let us also consider a distribution tau from the property P that we are considering. And let's assume that theta is a good detailing of tau. Now, since the detailing theta of tau is good by the couple of previous slides, we know that it is predictable, so we can run the canonical tester to approximate the acceptance probability. So now we have two detailings chi of one for the input distribution and a good detailing zeta of tau, another distribution in the property. Now how do we connect these two distributions? So we use the statistics of the detailing to estimate the distribution distance between these two distributions, and the notion of inheritance crucially captures this notion and helps us prove this result. So in a sense, refinements, the inheritance captures the fact that the refinements of bounded size does not change the type distribution too much. And the notion of inheritance turns out to be like tied to the notion of robustness. So this is akin to the notion of robust partitioning in the regularity lemma for graphs. So detailing, we call it to be a robust detailing if we doesn't, if the marginals of the detailing doesn't change too much when we take a bounded size refinements. So for example, in this refinement of mu a to mu a b's, we will call it a robust detailing if these probabilities remain close to each other. And we further prove that robustness implies goodness. And by the previous couple of slides, we know that goodness implies predictability. So once we have a robust detailing, we can prove that it is good. It is a good detailing. And once the detailing is good, we can run the canonical tester to approximate the acceptance probability. Okay, now we have the notion of robust detailings. So in order to formally underpin how this detailing, robust detailing works, we define the notion of the index of a detailing, which is again similar to the index of a partition in graph regularity lemma. And in a sense, index of a detailing captures how much information the detailing gives on the distribution. So we show that if our detailing is robust, the type distribution doesn't change too much when we consider only bounded size refinements. And we captured this by estimating the index of the detailing at the very beginning and after doing a bounded size refinement. So to check whether a detailing is robust, we need to estimate the index of a detailing. So we design a suitable subroutine for this purpose. And once we have this subroutine, given any detailing, we can use this estimation of the index subroutine to detect whether the detailing is robust. Now, once we have the subroutine for testing whether a detailing is robust or not, we use that subroutine further to find robust detailings by running over multiple possibilities and checking whether those detailings are robust or not. Now, unfortunately, estimating the index of a general detailing is difficult. And this is primarily due to the fact that we are obtaining samples from the unknown distribution. So to tackle this, we consider refinements of a particular type. So we can only consider refinements by fixing variables or fixing the subcubes of the underlying Hamming cube. And we call the detailing to be weakly robust when we consider only refinements by fixing variables. Now, of course, the question comes whether these two detailings are close to each other. And in fact, we proved that weakly robust detailing implies general robustness up to parameter change. So to sum up, our final distance estimation algorithm has 5 parts. So at the very beginning, we find a robust detailing chi of distribution mu, and then we estimate the statistics of chi. which gives us the weight distribution eta and the type distribution lambda. And once we have the statistics of chi, we consider all possible hypothetical detailings corresponding to distributions in the property. So once we consider the hypothetical detailings, we first run them through the canonical tester to approximate the acceptance probability. So once we have the set of possible hypothetical detailings which can be accepted by the canonical tester, we test them against the statistics of chi, and at the end we output the minimum distance among all possible like pairs of distance that we have obtained. And this distance is the good approximation of the original distance of the distribution mu from the property P. And we show that all these steps can be done only by performing only constant number of queries. So just to be clear, this brings index invariant property under the umbrella of all properties where constant testability implies constant estimability. And secondly, the dependence on 1 over epsilon is only doubly exponential, not a function of tau. So to conclude, this huge object model is a very recent model with lots of potential applications. And in this work, we actually proved that testing and estimations of index invariant properties both can be done using constant number of queries in this model. And recently, there have been several works studying various notions of adaptivity, testing of support size, testing of uniformity in this model. And it will be very interesting to see new notions in this model. Thank you for listening.